Okay, I want to talk about an interesting parameter that I can use to describe and design fins. It's called the fin effectiveness. Okay, so once you know the heat transfer rate from a fin, which we've been talking about, you can consider the fin effectiveness. This is very straightforward. We're going to use this term epsilon, which is the fin heat transfer rate divided by the rate if there was no fin. Okay. So you can look at this diagram here and see this. Okay. So this would be a surface with a fin. This would be that same surface if the fin wasn't there. And we're talking about this surface. Okay. So it's just a small cross sectional area relative to now we've increased the surface area. But we're just talking about the location where the fin is. And so if you write this, heat transfer rate for a fin is just Q fin. We know how to compute this for various boundary conditions. The rate, if there was no fin, if we just took this, that's just Newton's law of cooling for this area. So it's HAC, which is the cross-sectional area, TB minus T infinity. And in this case, there's no HA fin or anything weird because it's just Newton's law of cooling because the entire surface is at the base temperature because that would be the base of the fin. So it's fairly straightforward. And as a design parameter, this should be greater than 2. Meaning if you're going to take the effort, in most cases, if you're going to take the effort to design a fin and put it on there, we should get at least double the heat loss we would get without the fin. So let's take an example for an infinite fin because the heat transfer is a little easier to write. So epsilon for an infinite fin would be HA fin TB minus T infinity. Okay, so this is what we said Q was for a fin. And now we're going to divide by HAC TB minus T infinity. So these temperature differences cancel out. HA fin was just equal to HPKAC to the 1/2. This is divided by HAC. So this is going to give us H and AC will go out, and so we'll get 1/2 for these. And then we're going to left with K times P over HAC to the 1/2. Okay, so how do we design a fin to be more effective? Well, you can increase K. So if we want to increase K, that makes sense because heat can diffuse down the length of the fin faster. So you got a higher temperature further down in the film. And of course, the higher temperature, delta T, would drive more heat transfer. You can increase the perimeter, which increases the surface area. You can decrease convection, which is kind of interesting, and decrease the cross-sectional area. Okay, so you want to make the perimeter large, but the cross-sectional area small. And so this is kind of interesting that fins are more effective at lower values of the convection, and that's the whole purpose of a fin. If you had excellent heat flow across this surface, then you would have good cooling. But when you want to use a fin is when you don't have good heat flow over a surface. So the idea is fins are more effective under conditions with very low H. So the idea is it takes it systematically improves a problem where you don't have good airflow. Okay, so you've got two solutions when you want to cool something off better: increase the airflow to it, or maybe you can't increase the airflow, in which case use a fin. So let's look at this car radiator. This would be an example. You've got hot fluid flowing in, and you want to cool it off. So you've got air blowing over some fins. Fins are more effective at low H. Okay, so let's write this. So why do you put the fins on the inside versus the outside? Fins are more effective at low H conditions. Put fins on outside for this example here. Okay? And the reason we're doing that is because look this, you can look at table 1.1 in a book. This we're using Fundamentals of Heat and Mass Transfer, Bergman and Levine, the 8th edition. You can look up typical values of the heat transfer coefficient or the convective coefficient For gas, it's 25 to 250 watts per meter squared Kelvin. And for fluids have a higher heat capacity, so they can really pull heat out faster. And they're moving at different velocities too. Boundary layers are different, so you get a much higher heat transfer coefficient, or the convective heat transfer coefficient. So that means that H on the inside of this pipe is going to be much larger than H on the outside. So if you have a design choice, you want to put the fins on the spot with a lower H to help heat transfer in this composite system. So that's it. That's just a little note on designing fins and thinking about how you can look at the parameters which help you design a better fin.